All right, everybody, I've got kind of a cool problem we're going to do today. And it's set up like this. I've got a three-dimensional coordinate system, X, Y, and Z, the usual engineering one. And then I've got this beam, and the beam starts at the origin, and it's fixed in place there. And the end of the beam is at negative 5i plus 3j plus 4k meters. It's just a different way for me to notate the rectangular format, so I don't have to write all the i's, j's, and k's. So negative 5i plus 3j plus 4k meters. That's the end of the beam. And then there's a cord attached to that beam, and the end of the cord is attached to a point up here and fixed in space. And that point is 9i plus 6j minus 2k meters. Right? So the tension in this cord extends from this point to this point, both of them fixed in space, and I'm going to say it has a magnitude of 125 newtons. And what I want to do is I want to calculate out the moment in or around O. I want to find the moment about the origin caused by this tension. And so what I'm going to do is I'm going to take the moment is equal to r cross t. And so the moment about O is equal to, and I'm going to use determinants. You can do this however you want, but I'm going to use determinants to solve this out. And I'm going to need the tension. So let's step back and let's find the tension. So I know that the tension goes from this point to this point. And let me go ahead and just label this point A and this point B. And so what I need is the position from A to B, which is the position of B minus the position of A. So that's going to be 9 minus a minus 5. So that's 14 in the I direction. 6 minus 3. So that's 3 in the J direction. And negative 2 minus 4. So that's negative 6 in the K hat direction. And that's going to be in meters. So that's the vector from A to B. But in order to find the tension, I need the unit vector. So the unit vector from A to B is equal to 14i plus 3j minus 6k. And then I'm going to divide that by the magnitude of this, which is the square root of 14 squared plus 3 squared plus negative 6 squared, which of course when I square it becomes positive. And that's going to be the square root of 241. And this is in meters and this is in meters, so the meters go away. So there is the unit vector pointing from A to B. And so the tension then, the vector tension, let me put it down here, the vector tension is equal to 125 newtons times square root of 241 is in the denominator, and then 14i plus 3j minus 6k. Again, no meters or anything in there because that's already dimensionless or unitless. Right? So 125 newtons times that. All right, so M0 is R cross F. So when I do my determinant, I, J, and K, I'm going to have R, so I'm going to go from, here's where the force is applied, right? The force is applied at A. So that R is minus 5, 3, and 4. So minus 5, 3, and 4. And then my force is right here. And so I'm going to put in 14, 3, and negative 6. And then, yeah, we have 125 newtons and then the square root of 241. So this is in meters here. And I'm just going to write 125 newtons over 241 all under the radical there. So that's going to be multiplied by the whole thing. So 125 over radical 241 Newton meters will be multiplied by this value. All right, so how do I get this? What do I end up with? So I got the I component. I'm going to have 3 times negative 6. That's negative 18 minus 12. right? So negative 18 minus 12, that's negative 30. So I get negative 30 I hat. And then the j, I take out, so how did I get the I? So I took out the row and the column. There's the column, there's the row. And I got this. So I got 3 times negative 6 minus 3 times 4. That's negative 30. Then I take out the j, and I'm going to get negative 5 times negative 6. That's 30. Minus 14 times 4, that's 28, 56. So 30 minus 56 is negative 26. So that's negative 26 j hat. And then take out the k, and I'm going to get minus 15 minus 42. So minus 15, oh, wait a minute. Go back to the j, that's 30 minus 56, which is negative 26, but j hat is negative. So that's going to be a positive value there. All right, then k hat is positive. So negative 15 minus 42, so that's negative 57. So negative 57 k hat. And then all of this is multiplied by that right there. But I just want to concentrate on the negative 30 plus 26, negative 57. And if you work all this out and you multiply it by 125 over the square root of 241 times all of that, you'll get negative 242 Newton meters in the I hat, positive 209 Newton meters in the j hat, and negative 459 Newton meters in the k hat. All right, so I'm not going to worry about that. But here's what I think is really cool. I did this by taking the moment about O with the force applied at A. But there's this concept called the principle of transmissibility. And the principle of transmissibility says I can take the moment along anywhere on the line of action of this tension. So the line of action of the tension goes from A to B and then infinitely out in that direction, infinitely out in that direction. So what happens if I take the cross product of R, but not R at A, I want to choose R up here at B. So I'm going to make my R vector there. The tension is in the same, it's going to continue out this way. But instead of using negative 5, 3, and 4, I'm going to use 9, 6, and negative 2. All right, so let's see what happens if I do that. All right, so the moment vector is going to be the same, except this R is going to be different. All right, so I'm going to pull this down. So I'm going to have 9, 6, negative 2. All right, so it's I, J, K, 9, 6, negative 2. That's still meters. And then I have 14, 3, and negative 6. 14, 3, negative 6. And that's 125 newtons divided by the square root of 241. Okay, so let's try that. And I'm gonna kind of ignore this for a while because I really don't need it. So if I do this, I'm going to have I hat, so I'm going to get 6 times negative 6, that's negative 36, right? Negative 36. Subtract 3 times negative 2, that's negative 6. So negative 36 minus a minus 6 is going to be positive, is going to be negative 30, right? So negative 36 minus a minus 6 is going to be negative 30. That's in the I hat direction. And then take out the ijk, and then the j, I'm going to get 9 times negative 6. That's negative 54, right? 9 times negative 6 is negative 54, minus 14 times negative 2 is negative 28. So minus a minus 28. And so that's going to be 54 plus 28. So that's 26. That's negative 26. But j hat is positive, is negative. So negative and negative becomes positive. 26 j hat. And then finally in the k hat direction, I'm going to take out the k and the ijk. I get 9 times 3, that's 27. Minus 6 times 14, that's 60 plus 24, is 84. Minus 84. And so that's going to be 54 plus 3, 57. Negative 57 k hat. So 30, negative 30, positive 26, negative 57. Right? Negative 30, positive 26, negative 57. If I go over here, negative 30, positive 26, negative 57. I get the same value for the moment, whether I chose R to be over here at A, or if I chose R to be over here at B. All right? So here's your engineering challenge. Find the midpoint of these 2 points, A and B. Right? You just add the 2 points together, divide by 2, and find the moment if I choose the midpoint of that string, the midpoint of that cable, as where my R is going to be, right? And you should get the same answer. So that's just my engineering challenge for you. All right, so that's the whole concept behind the principle of transmissibility. Doesn't matter where you choose along the line of action of that tension to do your R. So why is that important? Because some points are easier than other points. And so choosing an easy point is going to make your work a lot less. All right. If you have any questions to that, please put them in the comments below. Thank you.